Due to its low boiling point and its inert nature, there is a high industrial demand for helium. As you can see, it is used in many applications. However, there is currently a helium shortage, as many companies avoid the recovery process due to high capital requirements, market volatility, and the dominance of a few top suppliers. The large demand for helium has had a major impact on the global market. Annual global demand for helium is approximately 6 billion cubic feet, which is expected to increase to an annual 8.5 billion cubic feet by 2030. We were tasked with designing a system that processes 50 million cubic feet per day of pipeline gas at 800 psig. The natural gas had to be delivered at 1,000 psig with less than 2% nitrogen content, at least 65% helium purity, and 96% helium recovery, ensuring compliance with environmental regulations.
So here's an overall view of our PFD. It's broken down into two major sections, our crude helium process and our helium purification process. The first step that we're going to take you through is the crude helium process, which is broken down into a few major parts, which includes the nitrogen removal unit, helium recovery unit, methane removal units, and then our heat exchanger network, as well as our feed, our methane sales gas, and our two nitrogen sales gas streams. The first major unit op is a nitrogen removal unit, which is a distillation column that separates our inlet natural gas stream based off of the boiling point. We are operating at cryogenic temperatures due to helium having a very low boiling point at 4 Kelvin, nitrogen having a very low boiling point at 77.4 Kelvin, and methane, which is the lightest hydrocarbon, having a boiling point of 111 Kelvin. Due to these really low temperatures, we are operating at a very high pressure as well to raise the boiling point to lower our operating costs. In our distillate stream, it is very heavy in nitrogen, methane, and helium, and that's just the methane that didn't liquefy with the rest of the bottoms, which is all the heavier hydrocarbons like ethane, propane, and methane, and the remaining nitrogen that was not vaporized. The distillate of the NRU goes into our second major distillation column, which is the helium recovery unit. The main purpose of this is to purify the helium out of that stream to get us our crude helium product, which is 70.79 mole% helium, meeting and exceeding our project requirements at 65%, while the bottom stream contains all the rest of the nitrogen and methane that was not vaporized. The next major portion are the last three distillation columns in our system, which is the methane removal units. The main purpose of the addition of these columns was to decrease our methane emissions into the atmosphere. Last semester, the bottoms of our NRU were directly emitting into the air and were releasing 24,000 tons of methane per year. Therefore, with the addition of D5, it helped purify the nitrogen to get it to a 99.99% purity, which we're now able to sell at an industrial grade, while purifying the bottom of the methane to be able to be added back into our sales gas. The bottom two columns, D2 and D3, essentially do the same thing for the bottoms of the NRU, while the first one's main purity, D2, is to purify the rest of the nitrogen out of there to get us below that 2 mole% content of nitrogen in our sales gas stream. All three bottoms are put into a mixer and then are sold back to a natural gas plant as our sales gas. Lastly, we have a turbo expander and a compressor. This is for our sales gas, as it has to be returned to the pipeline at 1,000 psig. The main point of the turbo expander is that the inlet has to be depressurized while the outlet, or sales gas, has to be pressurized. So the work shaft generated from the turbine is being input into the compressor to help decrease our overall energy uses in the system, while there's also excess energy still needed for the rest of the pressurization, which is the additional compressor at the end.
So our system has several heat exchangers. Because we have so much cooling duty requirement because of the cryogenic temperatures, we implemented a heat exchanger network which uses recycled streams to recover as much heat duty as possible. So you can see that our feed runs through that ambient exchanger entering into the purification system, and then it basically goes through all of the column reboilers to provide the heat duty. And then we also have some cooling duty recovery. So the bottoms of all of the methane purification systems work to cool the inlet feed down to cryogenic temperatures. And then we have the distillate from both the HRU and the HRU methane removal unit that work to provide some cooling duty to the second methane removal condenser. Overall, the addition of the heat exchanger network, rather than just using utilities for all of the exchangers, provides about a 45% reduction in utility use cost. So the second part of our process is the helium purification process. For this, we use pressure swing absorption. Our first part of our crude process primarily uses distillation as the separation mechanism. The reason that we're using PSA for the helium purification is because once you get into the higher purity helium, it becomes difficult to separate out using distillation. We were able to bring our purity up from the 70% at the end of the crude stage to 99.99, which is grade A helium, and we also ended up with a recovery of about 83%. PSA uses physical adsorption. So if you're looking at this, where the smaller molecules represent helium and the larger molecules represent hydrogen, you can see that the hydrogen adsorbs to the sorbent while the helium, for the most part, is pushed through the system. And this has to be done at a high pressure to basically force those molecules onto the adsorbent. In our system, we had to do two different types of beds, one to remove nitrogen with the adsorbent as zeolite 5A, and then two to remove hydrogen, which we're using a lithium nickel adsorbent since they have different capacities to absorb the impurities in our crude helium stream. So really quickly, the PSA, we're using a 4-step cycle.
Step 1 absorption, Step 2 blowdown, Step 3 purge, and Step 4 pressurizing.
Finally, in our PSA system, because we're on cycle timers and all of the beds, we have 6 beds total, all of the optimized step times are different. So we have to use some process control loop, and this allows for the feed to fill up that level, and then once the level is high enough, the level controller can alert the valve essentially to open and the bed to pull feed once there's enough feed for the adsorbent step.
From the beginning of the project, our team has analyzed multiple decision matrices to ensure aspects of process and environmental safety were considered. As the process itself was designed, we constantly discussed concerns of both overpressurization and large amounts of hydrocarbon emissions being produced. To minimize overpressurization concerns, a pressure safety release system should be implemented. Pressure control valves should also be implemented as appropriate throughout the system, ensuring operating pressures remain within appropriate ranges. When the pressure of any unit operation reaches or exceeds a designated value over the equipment's explosive pressure, however, the emergency shutoff plan should deploy. The system should be cleaned of scale to meet API 510 standards, and it should be checked for damages. Other ideas were also explored to address operator safety concerns. So if helium is in such a demand right now, why are we not just selling our crude helium? So crude helium is going to be used for applications such as balloons, non-critical leak detection, and welding gas mixtures. Grade A helium, however, is a little bit more useful for laboratory applications. So now let's compare the economics. So for our crude helium process, we're going to have the large amounts of our equipment costs coming from our heat exchangers and our compressors. And then when looking at the bare module costs that include considerations such as valves and installation costs, we have a total equipment cost of about $40 million for our crude helium process. And when looking at the bare module cost of our grade A helium process, we're at about $48 million. So when looking at our yearly sales for our crude helium versus our grade A helium, we increase our sales by about $26 million. We do, however, increase our total manufacturing costs by about $7 million, our production costs by about $10 million. However, when we're looking at our internal rate of return, it's important to note that our construction is finished building in year 3. In year 4, however, both processes seem to be profitable, largely due to the high amounts of helium demand present.
Here's our summary of results. So the first thing was the nitrogen in the pipeline natural gas had to be less than 2%. In our crude helium process pre-optimization, it was at 6.2%. And what we were able to do to get to the final 1.89% was to add those methane removal units. The project constraint of a 65% helium purity. Right off the bat in our crude helium process pre-optimization, we were able to get to a 70.79% helium purity, which was even elevated more to 99.99% with the PSA being added. As you can see, our final crude helium process with the PSA had a lower helium recovery, but we were able to get that higher purity. And also we were able to get the helium recovery constraint met when we did the crude helium process. Further recommendations for this project would be opting for a 2-bed PSA design that will allow for pressure equalization between the beds, removing the need for extra compressors, which will also likely increase recovery.
Thank you for watching.